Welcome back to chapter 8. We're going to talk about E2 versus E1. Really dive into the mechanism here. And see what we can do. 8.4 is the section we're on. We're going to show some energy diagrams, talk about mechanism in detail here. Eight point four. The E2 mechanism. Let's start with E2. There's going to be some analogies we can draw from SN2 to E2 and SN1 to E1, but there'll be some differences. So let's take a look at this. Let's put in our stereochemistry now. We'll talk about this orientation of the hydrogen and bromine bond at the alpha and the beta positions. Talk about it a couple times. Right, this is our alpha carbon. This is our beta. And we're going to deprotonate the beta hydrogen. Okay? So we're going to use sodium hydroxide. Okay, this is a strong something. It's a base or a nucleophile. Because this is a tertiary, we're only undergo elimination. Okay, I'm kind of giving you practice as we go. The E2 is going to look like this. The OH minus is going to orient itself near this beta hydrogen. Any one of these three could be deprotonated, but these bonds are going to align in an anti-periplanar arrangement. Okay, that means they're in the same plane and they're anti to one another. They're kind of pointing different directions. Deprotonate, and the point here is this orbital overlap. Okay, we talked about anti-bonding orbitals and things like that. Keep in mind this carbon-bromine bond is an sp3 bond. There's an anti-bonding lobe back here that is an empty orbital, okay, or it is an empty orbital. Remember, we've talked about these, so you don't have to explain all this, but the idea is there's donation, so to speak, into that orbital. This is the most favorable arrangement, the anti-periplanar, and that's the argument for it, okay? So I just want to give you some argument for why it's anti-periplanar. We're going to deprotonate, electrons push down, you're forming a pi bond. These electrons are leaving with the bromide. And what do you get? You get an alkene. Plus water and sodium bromide. Bond breaking, CH and CBr, is simultaneous with bond forming, the carbon-carbon double bond. Concerted, no intermediate. Transition state, no intermediate. Okay, they're different. So no carbocation. So let's look at kinetics. We've said this, but let's say it again. E2 is second order bimolecular. Okay, so that means the rate equation involves both pieces. K is always generic for our purposes. We have a tert-butyl bromide. That's what we started with. So the concentration of the alkyl halide and the concentration of the base. Bimolecular. Okay, they both have an exponent of 1. Together, that's 2, and it's bimolecular. So if you increase the concentration of sodium hydroxide 2 times, you increase the rate 2 times. If you increase both of these 2 times, you double the concentration, then you increase the rate 4 times. All right? So keep that in mind. Again, there could be a simple problem in that sense of 2 or 3 or something like that. Let's look at the single-step mechanism. Okay? Let me show you the transition state on this slide. The way to draw a transition state is to put in everything that is unchanged, similar to a resonance structure, or a hybrid rather. When we draw the resonance hybrid, we put in everything that hasn't changed. What is changing is the bonds that are breaking are the H and the Br. They're half bonds. The bond that's forming is the pi bond. It's a half bond. We're forming an oxygen-hydrogen bond. That pair of electrons is now interacting with that H. There's a delta minus here. And there's a delta minus there. Okay, with 3 lone pairs. And this dashed line indicates a partial bond breaking. We have this whole thing now is, and really, technically, there's a sodium plus associated with this whole, there's -1 charge on this whole thing, right? The sodium plus. Truth be told, there's even more complexity to this. There's probably multiple sodiums involved, etc. There's probably a sodium associated with this partial minus and a sodium associated with this delta minus, okay? That's the transition state. And you should be able to draw that. It's more challenging, I think, than the SN2. So SN2 or E2, you should be able to draw those transition states. The single step mechanism is concerted, so the energy diagram looks like this. This is exothermic. Tert-butyl bromide is going to alkene. It's an elimination. We're eliminating a molecule of HBr. We have a transition state here. Where's the activation energy? There, EA, energy to get over that hill. The thermodynamic term is delta H, and that is the difference between the starting materials and the products. This is exothermic. Okay. Where's the transition state? It's at the top of the hill. Again, you should be able to label that transition state at the top of the hill. Okay, so that's the energy diagram and the transition state. Let's look at the base, okay? Just like we had with substitution, a strong base is going to favor a concerted reaction. It's going to favor that substitution SN2 with a less sterically hindered alkyl halide and a stronger base. So we're going to see the identity of the alkyl halide is a little less important in elimination, okay? Because both eliminations, E2 and E1, are going to increase with more steric hindrance, and we're going to explain why. Okay, so really we're looking at base strength. Base strength is the big category here for elimination. Base strength, the base strength impacts the rate, E2. So you can have an O minus or an O minus, like we've discussed. We've shown a lot of those. Sodium hydroxide, potassium tert-butoxide is that non-nucleophilic base. Sodium F oxide is both a base and a nucleophile. Okay, so you can have these inorganic bases. You can also have two that are very similar. Okay, I'll show them both to you. This is called DBN. Sorry, DBN for short. You should get used to these abbreviations, but I would give you the structure. It's called diaza for nitrogen, diaza bicyclononane. Okay. The idea here is this is neutral by formal charge, but you've got this lone pair pushing in, so you can draw a resonance form that puts even more negative, partial negative charge on that nitrogen. Okay. So this nitrogen is more basic than a typical amine. Okay, so a nitrogen with 3 bonds around it. So it's a strong base, but it's a hindered base. It's a good non-nucleophilic base. So I want you to memorize these non-nucleophilic bases: potassium tert-butoxide, DBN, and DBU. Okay, DBU is almost identical. But it's a 7-membered ring here instead of a 5. Diaza bicycloundecane for 11. Okay? DBU, a lot simpler. Okay, both of them are non-nucleophilic bases, so memorize those in terms of not having to draw the structure, but seeing them, knowing what they're going to do. So if we say a non-nucleophilic base, what do we mean? We mean that the non-nucleophilic base, it's strong, it's going to cause deprotonation. E2, conserted. What do we get? Alkene. Okay. Draw the products of these, you get something like this as your byproduct. Plus charge there, Br minus. Okay, that's your byproduct, BP. It's an organic byproduct, but we're really looking at the alkene. Okay, so you should recognize those. Those are E2. Leaving group, same discussion as with substitution. I'm just going to say it. The I is more polarizable, so it's a better leaving group. Okay, so it's going to increase the rate of E2. Again, for our purposes, I really want you to think of Cl, Br, and I as good leaving groups. Okay, so it's going to increase the rate of E2 as you go down that series, but it's not a huge issue. Okay, so leaving group Cl, Br, I. I is more polarizable, better leaving group. Okay, so I minus is a very good leaving group. Solvent. Okay, same kind of passing point. You're going to see polar aprotic solvents and polar protic solvents. So the same idea as with a bimolecular mechanism, of polar aprotic solvents do not solvate anions well, therefore the strong bases are not inhibited. Okay, so if we have a strong base, an O minus, we don't want a proton. That's the point. So let's look at something like this, potassium terpbutoxide, strong base. We don't want to have methanol or water floating around there because that's going to pick off that proton. Okay, so that's why with strong bases, you want aprotic solvents. Polar, but aprotic. Okay. For weak bases, we'll talk about that with what do you call it? E1. Okay. So acetonitrile, right? Ether, the same ones we gave before. These are good solvents, polar protic solvents. DMF. They have dipoles. DMSO. It's DMSO. That's DMF. Okay, same ones as before. Now the alkyl halide, as I mentioned, as we increase steric hindrance, it's going to increase the rate of E2. So let's refresh here. We have primary, and of course, methyl alkyl halides cannot undergo elimination. They have no beta hydrogen. Okay, so here we're just looking at primary, secondary, and tertiary. Right, we said the SN2 increases here, whereas E2 increases, increasing rate of E2. Okay. Now, the way we justify this, okay, sort of, that's the data we observe, is you have more substitution, the tertiaries, et cetera, you're going to increase the rate. The way to think about this is that you can draw the transition state, right? What do we have? Just like we showed before, the transition state resembles a more substituted double bond. If there's more alkyl groups on the alkyl halide, then the transition state is more highly substituted alkenes. Are more favored. Okay, so that's the argument. There's probably weaknesses in that argument, but that's the argument. Okay, increasing stability of double bond, increasing stability of transition state. Okay. Again, you may need to draw that concerted transition state. Those are the two transition states that you should know how to draw: SN2 and E2. Okay, the other ones we talk about, but those two you need to be able to draw. All right, so let's kind of discuss this rate idea with a couple examples. There's our beta hydrogen and our alpha carbon. Okay. So we have some sort of base, some RO minus, okay, deprotonate, form a double bond, kick out the bromide, right? What do we get here? you get a mono-substituted alkene, one alkyl group, right? Whereas with this, tertiary alkyl halide, same idea, still E2, but now we have two alkyl groups on this tertiary instead of a primary, and we get a di-substituted double bond. This is going to be faster, slower. Okay? Rationalize that by the substitution of the transition state. Okay, so E2 review, second order, one step, concerted, increasing RX substitution, tertiary fastest, better leaving group faster, strong bases, polar aprotic solvents, and the stability of the alkene, or the transition state rather, is going to impact that. Okay, so let's talk about possible. What if there are multiple elimination products possible? Okay, so 8.5 is the Zaitsev rule. A very important rule. Just following the book for my outline. Zaitsev rule helps us predict the major product is the more stable double bond, more substitute. Again, you just need to memorize that. More substitution, understand the why, but memorize it. Okay, so now we have two possible products. And you may be asked, and you will be asked, to decipher between the major and the minor. So now we have an iodide. We got alpha, beta, beta, beta. We have two different types of beta hydrogens, three different sites. So sodium hydroxide, I'm not going to draw the mechanism on this one. We have two different possible products. Okay, I'm going to draw it both ways. These are the exact same thing, just so you see that. Either of these give this product. Okay, it's methyl cyclohexene. Okay, these are equivalent. They're the same thing. The other product, though, is an exocyclic double bond, a di-substituted. So you have a tri-substituted or a di-substituted. This is the major. You may have to draw both and circle the major, for example. This is a concept called regioselectivity. Okay? We talk a lot about selectivity in this class. Okay, so it's selecting a region. This region is eliminating, not this region. Okay, so it's regioselectivity. Again, the Zaitsev rule can be explained by transition states. Okay, so if we have the less stable or the more stable transition state, you can imagine it correlates with the double bond. Okay, we don't need to draw these out. Maybe we'll do that in class. You don't need to draw this explanation, but you need to think about it to predict products. Again, you're going to memorize more substitute double bond product. Okay, but you could draw out the transition states for each of these, and it's the point is they correlate. Okay, that's the explanation. So let's look at a couple other examples of major and minor. Okay, we will use this aromatic substituents from time to time, just to have substituents on our carbons to give a little variety. So we have a couple aromatics. Here's our beta. Got to have that beta hydrogen. KOH is a strong base, also a strong nucleophile. This is a secondary. We're going to get into that later as how you would decipher between substitution, elimination, or whatever, but you're going to lose KBr as a byproduct. You're going to lose a molecule of water. And what do you get? Phenyl is the abbreviation for those rings. And you get cis and trans. Which one do we say was more stable? The trans. That's the major. Minor. Same idea with a ring. Chloride. We have two different types of beta hydrogens. Let's call this beta 1, beta 2, KOCH3, potassium methoxide, minus KCl. There's a byproduct minus CH3OH, methanol. Okay, walk through the mechanism of all these. Okay, so we have two options to deprotonate. Beta 1 gives a tri-substituted double bond. Beta 2 gives a di-substituted double bond. Major is the tri, minor is the di. Okay. All right, that's E2. Let's try to conquer E1 now. Okay, E1 mechanism 8.6. Again, E1, that one is really important. It means first order unimolecular. Kinetics, the rate is simply the alkyl halide. Whatever the Rx is, that's it. So the base can be very, very weak. So let's go over a mechanism. Okay, we'll show the mechanism and then we'll talk about the energy diagram. So we have a tertiary alkyl halide, and we're going to see that E1 also follows the trend of more substitution. Faster rate, but it's going to be because of the carbocation. Here we're going to form a di-substituted double bond, okay, and we're going to form molecule H3O plus and I minus. This is related to that SN1 mechanism, and you're going to see actually that this can go either direction. We'll talk about that. First step, rate determining, heterolysis, bond breaking. Because this is weak and because this is a tertiary, there's possibilities of forming a carbocation. We have 3 CH3s around this. Again, what's it actually look like? You don't have to draw p orbitals and things like that unless I specifically ask for it. And I won't ask for it in a mechanism question. It's unlikely. Usually it's a separate thing. But in any event, you get carbocation, empty p orbital. Okay, what's that mean? It means these electrons here in the sp3 hydrogen 1s bond are much, much more acidic. In a very weak base, such as water, can deprotonate, push the electrons down, and satisfy the electron deficiency of the p orbital. What's that give you? It gives you two p orbitals filled with a bond, a pi bond, new pi bond, and you get H3O plus and I minus. I minus is associated with the carbocation. Okay, so you got to be able to draw this out. And we're going to see that E1 and SN1 compete. Okay, we'll deal with that later. Let's look at the energy diagram for this two-step process. This is exactly or very similar to figure 8.6, so I'm going to abbreviate some things. Material, alkyl iodide. We have our products. The reaction overall is exothermic. We have an intermediate carbocation that has dissociated. That's a high energy intermediate, but it can form. That's step one. You can draw the transition state. Again, look at figure 8.6 to see that. And there's a transition state one. This is the rate determining step. That's the high energy species. There's a thermodynamic, endothermic nature to that. And then you have the second step is fast. Fast step. Transition state 2. Okay. So carbocation is key here. And then overall, exothermic. That's an exothermic step. That's an endothermic step. Okay. So work through that, understand that. I'm not going to make you draw that whole thing. I may ask you to assign parts of it or things like that. You need to understand those. I may ask you to draw simple energy diagrams, okay? But increasing rate of E1. Now the same trend for both eliminations. Still got to have a beta hydrogen on that R group. The idea is primary, secondary, tertiary, we have increasing rate of E1. But the explanation is different than for E2. Increasing rate of E1 corresponds to increasing carbocation stability. By now you should be very familiar with carbocation stability increases with increasing substitution. Okay. So let's do a little review here. Strong bases favor E2. Again, we're going to get into this deciphering between the 4 reactions. Right now, we're just looking between E2 and E1. Strong bases, such as O minuses, NaOH, KO terpenoxide, or OR in general, metal, OR, DBN, or DBU, favor E2. DBU favors E2. You better remember that. Okay, weak bases, mainly we're talking about water and alcohols. Okay, they favor E1. So E1 also follows this Zaitsev's rule. Okay, so you can kind of memorize that is elimination. E2 or E1 is going to favor the more substituted alkenes. Again, you should be hearing that very, very loud and clear. You will have to know that. All right, so let's look at one more mechanism just to review. H2O, excess. Doesn't really matter if it's excess, actually, but whatever. There's 2 possible products. What I'm going to do is give this as a take-home mechanism. You can get the tri or the di substituted. Okay, so work through the mechanism. It's E1, so I'm telling you what the intermediate is. Work through that. And maybe we'll go over it in class or whatever. So E1 is first order, 2 steps, carbocation intermediate. Higher substituted alkyl halides react faster. Again, not such an important point. Weak bases, that's very important. Better leaving groups favor E1. Again, not a huge factor, but the weak base is really important. Polar protic solvents are necessary, same as in nucleophiles. So the polar protic solvents are going to help stabilize that carbocation, just like SN1. We're going to see a lot of connections between SN1 and E1. Okay, we'll see some connections between E2 and SN2. So that concludes this lecture.